Welcome everybody to the RoboRIO and Sensors presentation. My name is Paul Ngo and I'm 1678.
And I'm Ellie Haas. I'm a mentor for 5499.
So we're going to start with sensors because the sensors are pretty much what give the RoboRIO inputs. A sensor is a device that detects and measures a physical property and records, indicates, or otherwise responds to it. So this is very important for creating a robot that's actually competitive. So a robot that just responds to driver control and what you can see on it won't be a very strong robot. Robots that use sensors will be able to detect where its parts are within the robot, parts outside of the robot that are being intaked into the robot, and also be able to run an autonomous mode that is strong.
So as Paul just said, why we use sensors are, one, to get feedback for positioning of robot parts internal to the robot. So if you have an elevator or something in your robot or a turret and you want to know exactly where it is, you can use encoders and limit switches to get, you can use a limit switch or a Hall effect sensor, something to give you an absolute value from which to start, and then your encoder will give you values around that. So you can get very precise angle measurements. So motion control. You have most people have encoders on their drivetrain. So at the moment on 5499, we don't actually have ours set up. So we are going entirely based on timing, and that causes problems because if one wheel gets pushed up and starts spinning, we don't know exactly what's going to go on. So if you have encoders and they can stay on the ground more or less, then you've got a much better chance of figuring out exactly where your robot is correctly. And on top of that, at another level of complexity, you can use a gyroscope and accelerometer that both make your positioning significantly more accurate. You can detect field elements in and out of the robot. So this is a diagram of the 1678 robot from Recycle Rush. So for Recycle Rush, you had to intake a tote into the middle of the robot and then start stacking them. So there were a couple different sensor setups that we used, or we considered to, oh yeah, I was a 1678 mentor last year. So we considered some different sensor setups to see if the tote was actually correctly positioned within the robot. So you could use a proximity sensor to say, oh, there's something within 10 centimeters of this sensor. You can use a line break, which is a line break sensor, which is essentially what you have in your garage. When you interrupt this laser beam, then you know that something is in between these 2 points, and so you know a tote has been put into the robot. This was another proximity sensor. You could also use a limit switch back here and hope that when a tote rams back into it, it pushes the switch down and doesn't actually knock the switch out of the way. Yeah, and then at the highest level of complexity within FIRST, you can use vision tracking systems. Generally, there will be something in a game that uses reflective tape, which makes vision tracking as easy as possible. Yeah, vision adds a whole nother level to things. Okay, implementation. So when you're mounting sensors, it is critically important that the sensor is protected from other robots, and if your robot flips over or sort of falls in on itself, something comes on top of it, that your sensors are not going to be knocked off. The sensor must be able to see the target. That's sort of obvious. If the sensor gets knocked out of the way, your whole robot code may cease to work. The sensor has to be secure. It is really important that you're able to easily remove the sensors. So that means do not solder your sensors all the way from the RoboRIO to the end of the sensor. It's going to make your life a lot easier if there's a connector somewhere near the sensor so that if it breaks, and on 1678, Hall effect sensors and apparently this year encoders have been breaking, so being able to quickly swap those out is critical. Noise. These robots are a very noisy system. They, the motors that you have running to control the robot and to control the arms, those create magnetic fields and electrical fields that will interfere with your sensors and the signals that go from through the wire from your sensors to the RoboRIO. So, if you have a sensor that seems like it's giving you inconsistent data, one, try running it and see if you get better data if your motors are off, and two, try moving the sensor to another location before you give up on it. Faraday cages, which, does everybody here know what a Faraday cage is? Some people? Okay, so if a person were to stand inside of a metal box and lightning were to strike, you wouldn't get hurt as long as the metal box was even if it's a cage, just with fine mesh. Electricity will go from one side of the cage to the other without affecting anything inside of it. So it's called a Faraday cage because I think Faraday discovered it. So that will protect your sensors from electrical interference. It will not protect them from magnetic interference. So on the plus side, that means your Hall effect sensors, which rely on detecting magnetic fields, will still work inside of a Faraday cage. On the negative side, that means motors, which produce a magnetic field, are not going to, they will affect sensors like a compass, and there's not really much you can do about it. So, different types of interfaces. The easiest interface to use is a digital input-output. So that's Boolean. It's either on or off, and in electrical terms, it's either 0 volts or 5 volts. Those are the only inputs that that sensor will send to the RoboRIO. So the advantages to that is that it's very easy to use and interpret. It's very hard to interfere with that sensor with noise. It's much more likely to be consistent. On the downside, it's not actually giving you very much information very quickly. So it can be incredibly useful. It has some limits. So analog sensors will give you more information because instead of just 0 volts and 5 volts, they can give you any value of voltage in between. However, they are much more prone to noise. And generally, analog output sensors are not going to be that precise. So a potentiometer, a variable resistor that spins, is going to
resistance over not a straight line, but rather a curve at the beginning and a curve at the end. It won't be very accurate.
yeah, and instead of a pretty line like this, you'll probably have a whole bunch of little bumps and stuff in it. Okay, so digital serial is trying to get the best of both worlds. So using a serial protocol is how computers sometimes still, it's a protocol that computers use to communicate. So it's capable of getting a lot of information very quickly. It should have the reliability that a digital I/O has, but be able to convey a lot more information. Yeah, the only downside to it is that it's going to be a little bit harder for your programmers to figure out how to analyze those signals.
Alright, so there are three main pieces of information that you want to figure out in order to choose your sensor. First are indicator lights. So most sensors have an indicator light for power, which you can use to determine whether or not your sensor is on or off. So in diagnosing problems, the first thing you can check is if when you turn your robot on, the sensor is not receiving power, then you have a problem with power ports or such. Secondly, a sensor output light is very common on Boolean sensors, so digital I/O sensors. So for example, Boolean Hall effect sensors, proximity sensors, possibly limit switches will output lights to tell you when they are being triggered, which is a very easy way to determine whether or not they are working. If you just trigger them with your finger or something, and be able to determine whether or not the RoboRIO is actually receiving the signal. So you can see if that signal wire is compromised. However, sensor output lights are not very common on analog and serial devices because a single light that can flash either on or off is generally not going to be very helpful if your analog and serial outputs are going to be flashing 1 and 0 very quickly, or a combination of precipitation and power working. Secondly, you want to determine your operating range for your sensor and how your computer sensor under distress these sensors need to have something in close proximity with the sensor. Optical conditions are very important. For example, light sensors that are things like lasers might not be able to detect glass very well or see the materials very well. Also, encoders can also get very inaccurate once you start speeding their shaft past their operating range. So you might want to note what your gear ratios are in order to determine whether or not your encoders will be useful for the application that you are using it for. Finally, there are some electrical characteristics of some of your sensors. 5 volts is very much preferred because the RoboRIO will output that, or possibly 3.3 volts. And 12 volts are also common for certain sensors, but you would have to route this off of the RoboRIO power port or use an extension cord, for example, 971s, which 1670 uses. Finally, accuracy and precision is important, but usually it scales with price. So if you want to determine exactly where your turret is, and then you use an encoder that's extremely precise with many ticks along its rotational axis, and then you'll then you'll be able to determine what sort of sensor that you want to use. Yes.
It says you need 12 volts if necessary. Could you just run off the 12 volts that comes from the DRM, or would you need to run?
Yes, you also can. Sometimes wiring might be a hassle if your VRM is in a specific place. So here's some examples of sensors. This, the picture on the top is a limit switch. It's Boolean because its output will be 1 if you trigger the switch and 0 if you do not. There is a high potential for mechanical failure. If you do not mount it properly, the limit switch will bend and go out of place or even snap off, including the switch on the top and the 3 prongs on the bottom. You can detect field elements very well, and it's extremely cheap. The Hall effect sensor, the picture over there is the one that we use, associated with that link right there, can be Boolean or analog. The Boolean version basically determines whether or not your magnetic field is strong enough for it to trigger, and the analog would be the strength of the magnetic field that's near it. It replaces the limit switch for a lot of applications because you can just have a magnet where you want to have the Hall effect sensors detect, but the price is a little bit higher than what the limit switches are. Somewhere around $10 for that specific sensor. So encoders are extremely useful to determine how fast you're turning a rotational part on your robot and how far you move that rotational part using some geometry. Their outputs are Boolean, which is a series of 1s and 0s alternating. And this Boolean information is actually more complex because multiple wires are used to transmit that information. And it will be able to determine where you are in the rotation on the encoder and what degree you turn on that encoder.
If you guys are interested, we have a slide at the very end that goes over exactly how an encoder works.
So encoders are a little bit more expensive than the other sorts of sensors. They range from anywhere cheap, such as $20, to extremely expensive ones, around $60. Some good ones that actually output an extremely precise pulse every 360 degrees. Yeah, so there's a wide range of choices to choose from if you want to use an encoder to determine how far you turn the wheel or something like that. A potentiometer, like we've gone over before, is analog, and it can help you determine rotational position along with the encoder, but it is highly inaccurate because of the slopes and the interference noise that it outputs based on resistance. They all have a limit. Alright, so we've got the gyroscope and the accelerometer, which we also have mentioned, which are extremely useful for determining how far your robot has traveled and changes in speed and angular velocity or angular speed. The gyroscope and the accelerometer are both serial outputs, so generally you can trust their signal very well. But the accelerometer on the RoboRIO is not very accurate, and you probably shouldn't use it. And if you want to use one, invest in another accelerometer off of the robot.
Yeah, for example, this chip is a combination of a gyroscope and an accelerometer.
Okay. Also, proximity and beam break sensors, which I've mentioned several times, are Boolean, analog, or serial, so they can determine how far away your item is based on analog or serial data, or they can be simply Boolean. If the object is within a certain range, then it will trigger. It's optical, so you must understand that there are some problems associated with determining how far away certain objects are, which are reflective in a certain way, or maybe don't diffuse light like other materials would. And proximity sensors and beam break sensors are usually relatively cheap. The RoboRIO. So basics of the RoboRIO is that the pins are spaced by 0.1 of an inch. So when you buy pin headers, 1678 buys them from, I believe, I forgot right now, but we buy them from several suppliers, but remembering that they're 0.1 inch spaced apart can be helpful for determining whether or not you're actually buying the right. So we should probably put RoboRIO. That's the user manual, and you can go back to it if you guys have any issues. CAN is the part of the RoboRIO that is wired up right here. And CAN stands for Controller Area Network. The Controller Area Network is made up of several nodes, which include motors, motor controllers usually, and several devices. And they all involve a CPU, which is a central processing unit, which will determine what messages it receives means, and be able to create messages in order to send along to CAN network. The CAN controller basically receives messages and stores them and sends them to the CPU when the messages are finished transmitting, or stores the messages from the CPU and transmits them once the CPU is done transmitting. The transceiver basically converts voltage from the CAN voltage levels, which are very high along the green and yellow wires, down to the levels where the CPU can handle.
So if you have to use the CAN bus a little bit with the RoboRIO. You need to use it to hook up, I believe, to the PCM and to the PDP. And there is a web interface that this link leads to that if you're going to be using it to hook up your speed controllers, that makes it fairly easy to figure out how to set addresses of all of your speed controllers and set the basic values of them. So I recommend using it.
So a CAN bus, what are the advantages of using that as opposed to running a PWM for say a motor controller or a sensor?
So here's that example exactly. So those are vectors, right? Speed controllers. If you were to wire straight from the RoboRIO individually from the speed controllers to the RoboRIO each individually, you'd have a lot of wires. Versus using CAN, you can just go down along each one in a sort of daisy chain fashion. This is sort of a picture on the bottom right there. This is how you should wire CAN, and the termination resistor is boxed in blue right on the power distribution.
Yeah, so if possible, always end your CAN daisy chain at the CDP using that termination resistor. It's going to make your life quite a bit easier. However, we found that if for some reason the connection like here breaks, you'd still get signals from everything, from all of your speed controllers and everything plugged in ahead of there, and even without the terminating resistor, yeah. So you'll still get signals from everything until the break.
Yeah, that's a specific design where it allows current to actually flow. That's usually a 120 ohm resistor.
Okay. I2C is a different protocol you can use to talk to sensors. It's widely implemented, and for FIRST Robotics, I don't know of any teams that actually use I2C to talk to sensors. It is possible, it's not going to be that easy. So the way I2C works is your RoboRIO will act as a master chip, and every sensor that you have hooked up to it will be what's called a slave chip. So the master will request information from the slave provide the information requested. So yeah, everything on the I2C bus will have an address. It will either be asking for a read or a write, and yeah, if you decide you have, or if you have a sensor that only will work with I2C, then you might have better luck actually using like an Arduino breakout board than doing it directly from your RoboRIO.
Or possibly finding another sensor with this blended to choose from. So I2C is actually used in a lot of industrial uses. LCD or LED drivers, EEPROMs, capacitive sensors, like clocks, digital temperature ICs, which would be funny to see on an FRC robot, and IR rangefinders.
So RS-232 is the official name for a serial connection, which we sort of talked about already. On the RoboRIO, it's just 3 pins, a ground, a receiving, and a transmitting pin.
Okay, so normally with RS-232, what you see up there is what might be plugged into, say, a VGA cable. You don't need to have that much information on the RoboRIO. What the RoboRIO actually only needs for the RS-232 connection is to constantly talk to the sensor when it needs to, and the sensor constantly giving the RoboRIO output on whatever it has. Also, it's nowadays not used in a lot of computers because there's an extremely high voltage swing. The voltage swing is between 12 volts, positive 12 volts, and negative 12 volts, which allows for highly reliable serial data, but that voltage swing is generally not good for generating fields. Alright, so this is the DIO connection. That's a PWM wire. There are 3 main pins on the DIO connection: ground, voltage, signal. Signal is white and is Boolean signal 1s and 0s. Voltage is constant 5 volts, which gives your sense of power, and ground is a reference point for both voltage and signal. So this is PWM, what those DIO pins are often used for. PWM is pulse width modulation, where pulse width of the 100% of a duty cycle, so 5 volts is 100%, is changed along how you want to have your motor or other sort of sensor be able to output power. So up there you can see that there's a 50% duty cycle which would run a motor at say half power, while a 25% duty cycle would run it at 4/5 its speed. Pulse width modulation is basically determining how long you want your 100% power to last in terms of its cycling. And its cycles are extremely fast, so that they're basically their average is what you see in terms of power. The 3 pins, voltage on the RoboRIO is actually 6 volts, ground and signal, which is a variance between 5 volts and 0 volts.
Computers will use PWM because it turns out to be much cheaper to have a computer only be able to output 5 volts and 0 volts than be able to input a variable voltage in between. So this is the cheap man's way of getting an analog signal that's anywhere between 0 and 5 volts. And it's effective enough that almost everything uses it.
Okay, so this is SPI, which is the serial peripheral interface. 1670 doesn't really use this, but it's a very interesting concept that we might be able to use in the future. It's another master-slave controller, where the SPI is the master, and it basically selects slaves. On the RoboRIO it's called chip select, CS, but in industry it's actually called SS, slave select. What it does is it determines what slave it wants to select. So SS1, SS2, SS3, and then it starts a clock. And with that clock, it starts, it initiates, after initiating the signal with its slave, it uses MOSI or MISO to take and receive data. MOSI is master output, slave input, and MISO is master input, slave output. So the slave actually gives data to the master at the same time that the master gives data to the slave. However, only the master can initiate the call with a specific slave. another way of wiring this besides each one parallel to each other, they can actually be daisy chained so that instead of data going across each other, so one to the master and one to the slave, they can actually go in a loop where all of the slaves and masters exchange information.
Okay, relays are fun. They'll have a 5-volt controllable output. They'll be able to go forwards and backwards. The relay actually moves a physical pin just with an electrical signal.
So the spike H-bridge relay, which we used to use, can actually break the motor by applying voltage across its two upper pins. So what that does is creates a sort of voltage break to break the motor. It can run the motor forward and run the motor reverse using basically only two inputs. 0, 0 might be breaking the motor, 0, 1 might be running forward, 1, 0 might be running reverse, etc.
The RoboRIO has an expansion port, which if you found that the pins that are available to you in the standard configuration aren't good enough, you can add a breakout board. And so that's capable of doing using VIO, I2C, PWM, and UART, which is just a different protocol. So if you decide you'd be interested in using a breakout board, there is one that's ready-made and that's sold commercially. That's what that link there is. It uses an Arduino that connects directly to the RoboRIO. And yeah, 971 has designed one. The Holy Cows has designed one. There are a few lying around, and if you're interested, you can probably get your hands on one.
Yeah, we specifically use 900 watts because it's very nice analog and such.
Okay, so here's everything that needs to plug into the RoboRIO at a minimum. So if you're initially programming the RoboRIO, you will plug into the USB Type B. That's sending information to the RoboRIO. There are USB host ports which are capable of powering and controlling USB devices. There's the Ethernet cable. You need to send the robot signal light through this pin down here. And
That's the Wade-Muller connection for the power of the RoboRIO.
yeah, power for the RoboRIO is important, and then the CAN bus is right there.
Database, what you would use. Okay. Thank you. These tabs is supposed to be part of the doc file.
And Paul also has a robot here that they're going to use that once people are done with questions, they're welcome to look at it and see how it's wired.